this lecture we are going to talk about MATLAB model development for fixed frequency digital control. This lecture is the continuation of the previous lecture. Here we will extend whatever we learned, the step by step MATLAB model development for digital voltage mode control, but at very basic level. Then we have shown a buck converter example with simulation. We will just show once again, and then we will show here MATLAB model for digital current mode control. So here in digital voltage mode control, in the previous lecture we talked about A to D converter, and we have already discussed how to implement this sampling block using enable and disable block, where we can customize the sampling point as well as the sampling rate. We have also discussed how to introduce delay in that signal. Basically, at what point should we sample? Okay. The next we will talk about mixed signal current mode control, because we have discussed in mixed signal current mode control your current loop is analog and voltage loop is digital. So we need to implement digital. So we need A to D converter, and since we are not using actually digital platform number, so it is a MATLAB version. That's why we do not need a separate D to A converter in the MATLAB simulation. But one can try it out, the model of a D to A converter, because D to A converter model is like a zero order hold effect, and that is already incorporated. So let us go to the MATLAB model of the digital current mode control. So here we have already discussed about digital voltage mode control in the previous lecture, so I am not going inside this block. But here we are talking about digital current mode control. So everything else is same, only this controller block is different. If you go inside, again there is a controller. I have used the same controller, but I will not use derivative action. So I will put derivative action to be 0, and you see z equal to 1, because if only PI controller we will see. So it is only, so PD, sorry, it is a not derivative, it is a P and I, because I am talking PD means discrete time proportional gain and KID means discrete time integer gain. So this is the representation of a discrete time PI controller. Okay. And then this is the reference voltage, and this is the A to D converter that we have discussed, and we can actually customize the sampling point here. So the sampling delay is inserted. This is the inductor current. So this block is common, this whole block, this block is common, all these blocks are common, analog domain, analog current mode control, only this block is different here, right. So this discrete time transfer function and this block. So that means this is a basic diagram where we are just inserting the digital block. Okay, now let us go and run the simulation. So here we are talking about the mixed signal peak current mode control, and if we want to increase the gain, let us say we are using a little bit higher gain, and we will see how the response look like. So this is a mixed signal current mode control, where we are basically using, this is the, we are sampling once per cycle, and there is no delay here. You see that is sampling exactly at the point of switching. Okay, but now we want to sample little bit earlier. So how to incorporate? So let us go back, and here we have TS. So in our code, let us go back. So we will hold the previous result and put TS equal to 0. Let's say 8 times T, and in the plot command we want to change the color. So this will use green color and red one, and let us run. So this is with the delayed version. Okay. So you will see the response is not fundamentally different, because it is already kind of sluggish response, but the sampling point is different. So if you see the green waveform and if you take these two particular update mechanism, you see the magenta one which we have done earlier, that means if we take only few cycles, you see the magenta one was getting updated at the switching point, which was the earlier case, but now the red one, where we have introduced a sampling delay, and that got changed. So we are sampling before the switch turns on. So, we have some around 0.1 t time, and that can be considered for ADC conversion time and computational time. So, you can keep on changing. So, the bottom line is this: by this block we are able to actually, that means by using this block we can actually customize the sampling point, and this will also enable, if you go for constant on time control or constant off time control, the event based sampling, the event can be created by this clock, and that will sample the output voltage. So, in summary, in current mode control, that means we are talking about analog current loop, but right now we are using this compensator as a transfer function, right? But imagine what will happen if your, suppose if you take a PI controller, how does it look like? So, PI controller is generally written like this: the output of the controller N is Kp into V error voltage plus UIN, and what is UIN? It is nothing but UI n minus 1 plus integral gain into error n. So, this can be simply, if you take the transfer function here, you can get this. How to get this? You will get Kp plus Ki 1 minus Z inverse, okay, and this block you will get. But right now we are simply plugging this transfer function. But what will happen if the Z inverse? What is Z inverse? Z inverse is basically unit delay, right? So, what is unit delay? That means it is defined with respect to some sampling clock. Now, if the sampling itself, if we want to customize the sampling age, that means we talked about we want to change the sampling point. Suppose this is my sampling point, I want to shift it here, that is one possibility. Then simply plug in this may not work, because if you go inside this block, it will ask for sampling time as if the whole computation will happen at that age. But we do not want, we want the computation to happen once the data of the ADC is ready. Since the ADC clock is shifted, so naturally the conversion time will be there and your data will be ready after some time. So, you need to start computing after that. So, this transfer function will not allow to customize the point of computation or point where to computation start. So, this cannot be done using just plugging this transfer function. So, in summary, if you want to customize that, I want to start computing once this sampling clock is actually sent to the ADC and the data is ready, then I will start computing. So, then you have to realize this. So, basically this UIN will be a register, that means you will have this kind of a register, there will be a clock, and register will store and pass data, and this register will behave like a Z inverse block. But whether this clock, that means we want to shift this register based on the age of the clock, not by this transfer function. Another point, we want to even change the sampling rate, because if we go for event based sampling, the sampling clock, the age will differ, maybe transient, their age to age will be different. Then under steady state, if there is any small perturbation, there will be difference in event based. So, for such cases, this Z inverse is not very straightforward, it cannot be implemented like this. So, there is no fixed sampling rate. So, we need to go for something called difference equation based implementation. That means we need to go for difference equation, that means we need to implement, that means finally thing we need to implement this transfer function using difference equation. How it is done? So, one of the example I have shown here, okay. So, if we use this difference equation, and then this will be delayed version of this, that means these two can be, if this is your un and un minus 1, this register can be used to delay this block, and at what point you will delay with respect to which clock, that can be synced with this sampling clock here. So, ultimately whatever we are implementing the digital control, straight away using this block is not a good idea. So, in the next lecture we will go further down and implement this controller using difference equation. So, in summary, we have discussed some aspect of digital voltage mode control MATLAB model, that was also discussed in the previous lecture. We have shown buck converter example, and this lecture we also talked about digital current mode control implementation, and we have realized that direct transfer function, importing direct transfer function is not a viable solution, particularly when you are considering the customized sampling edge as well as the varying sampling clock. So, we need to go for difference equation based controller implementation. So, in the next lecture we will talk about that aspect. So, for today, that is it for today. Thank you very much.